mid-90s, 95, I guess, he came to the lab. He's had a very long association with this department, a very fruitful one, even before we were happily a situation here formalized as a lecturer and now as an adjunct professor here. Lee was did his undergraduate work at the University at Rutgers, master's degree at Maryland, and then came back to Rutgers for his PhD with Joe Lechechevsky, who has produced many students who've gone on to work at the DOE labs, and Livermore has benefited from this particularly. Lee is a premier experimental nuclear physicist and a great pedagogue. As I say, this department's had a very beneficial relationship with him for many, many years. He's now, I think a year ago, contributed to kind of the pivoting of the US data program there, and is leading the thing called DEANS here, the Data Evaluation for Applied Nuclear Science here, of which Berkeley has now become a major hub, almost sort of co-equal with Brookhaven here. This is a marvelous new development, and Lee is doing some great things up at the cyclotron, at the high flux neutron generator, and also working at NIF doing plasma mediated nuclear physics. This is a very, very interesting cloaking he's going to give us today on the Baghdad Atlas, so I'm going to turn it over and let Lee get going here.
Okay, thank you, Carl. Thank you for that warm introduction. It's good to be here. It's intimidating to be in front of so many friends, which means I don't get to run away and have everybody, I don't have to deal with you all later if I get crummy colloquium. So yeah, it's a compelling title. I thought it was a neat topic to talk about, nuclear data from Baghdad to Berkeley. One of the things that I've discovered as I've become more involved in the US nuclear data program and its international counterpart in the International Atomic Energy Agency is actually how little people know about how nuclear data comes into its existence and how it becomes part of the applications that we do. So that's really important. Many of us aren't even aware when we're using nuclear data in some time. If you run NCNP, you're using nuclear data. Everyone sort of knows that. But they don't know how it comes into that picture. And so what I'm going to do is discuss that process. I'm going to give you a specific example of something that we're going through right now as part of the US nuclear data program, and that addresses some of those deficiencies that we see in a specific issue, which is neutron scattering. And then I'm going to end by discussing some of the experimental work that we're doing here in Berkeley using arrays all over the world to try to address some of those uncertainties that can't be obtained by better evaluation. So that's the outline of the talk. The first part, I'd say, is the origins of nuclear data, which is where does this stuff come from? And something that I've been telling my class in 101 all the time is that we can't accurately calculate anything of consequence to applications. We really can't. If we have the answers, we can interpolate, but we can't actually calculate it. The truth is, nuclear physics is very complicated. We have to measure everything, okay? We can then take small baby steps between measured quantities to try to understand what's going on. So what I'm going to do here is discuss how the sausage gets made and when it can go wrong, okay? And there's a nice example of one of these going on. So next I'll talk about some of the specific holes in nuclear data that we have right now, again, relevant to applications. We go to a lot of conferences in basic nuclear physics where we talk about this, where it's relevant to astrophysics. I'm going to focus right now on what's important to the applications here. And this is where those skeletons are hidden. Okay. Next, I'm going to go back to the Baghdad Atlas. So this is a piece of heritage data that we managed to get our hands on at Berkeley. It's quite old, so I've decided to call it, it's that 70s show of nuclear data. Okay. This is rolling back to a very, very long time ago, where sometimes you actually find some of the best data was stuff that was taken in the past, but just never made it into the evaluation process for any number of reasons. And then last, I'll discuss some of the work that we're doing here. DEANS is part of a larger effort, which we call the Bay Area Nuclear Data Group, or BAND. And I think it's in bringing in the best of the old and the new. We have some real talent in nuclear data evaluation that's a part of this effort. These are folks that retired from Lawrence Berkeley Laboratory who are part of our project, as well as a bunch of new folks, including students, graduate students and undergrads. Okay, so part A. There are 3 simple rules about nuclear data. The first one I just said to you, we can't model or predict any cross-section with the level of accuracy necessary for most applications. That's true. Now, we can model it, but if we don't have the answers to related problems, we can't actually do it accurately. So if we put in the right data, we can turn a crank and return back out data. We can fill holes between known measured values, but we can't, from first principles, calculate out a cross-section with a great deal of reliability. Now, some people who do basic science experiments will say, no, that's not true. I can go in, I can turn a crank, I can run case or some other code. There's so much background physics that's going into that model that you're using, okay, that had to have been measured by someone else in order for your results to be vaguely accurate. Okay. 2, honest, hardworking researchers can measure the same thing and come up with different answers. This really is the truth, okay? This is a complicated business, especially for certain types of nuclear data where our tags on the observable are not very good, okay? And so 3, we use post-publication review and evaluation to ensure accuracy and consistency. This is something we're very proud of in nuclear physics, that we do this post-publication evaluation. Not all fields do it. I'm avoiding the temptation to go in and call out some of the specific examples that have made the news headlines lately in biology, where there is a significant amount of irreproducibility in data. So we try to avoid that by going through and doing post-publication review and evaluation, and that's where the nuclear data program lives. So let me give you an example of number 1 about prediction. So this is a plot, a very dramatic plot, I should say, that Franz Kepler from Karlsruhe showed at a workshop that we had a few years ago in London. This is a plot of neutron capture cross-sections on hafnium isotopes. Now, these are actually energy average cross-sections. They're measured over a Maxwellian distribution of energies at 25 kilovolts. And these are measured values that he has here for the different hafniums, 176, 178, 180. Okay? That's a log plot. And he did an interesting game. He went in and he asked the 6 leading modeling groups to go out and predict what he would get for the next 2, jumping 2 nuclides so that we can get rid of the effects of pairing, for the next 2 neutron-deficient and neutron-rich hafnium nuclei. So he said, I'm going to go measure these things. I'm going to do it in the accurate way that I'm used to doing it. I want you to write down, I don't think he actually said these words, but write down on a slip of paper, seal in an envelope what you think I'm going to measure. Okay? So the first thing to note is that if I asked somebody to do that, they'd laugh at me or throw stones at me. Okay? But Franz Kepler, you know, what can I say, a guy named Kepler who does astrophysics, you got to do what he asks you to do. Okay? So they did that. This is what they wrote down. Okay? Now keep in mind they didn't talk to one another. They came up with this distribution of points. There's actually an interesting story as to why things clustered quite close here and were quite different out over here, but I'm not going to go over that for the moment. Okay? So that's the range, roughly a factor of 3 and a factor of 6. Okay? And the goal in this particular astrophysical application was plus or minus 30% accuracy. The good news is that the answer did indeed fall within that middle range. The bad news is that if you were somehow designing an energy system or some sort of cargo screening system or anything with actual practical application that would matter, and you were asked to calculate one of these things without the help of experiment, you'd be in deep trouble. Okay? Because that's not accurate enough for anything applied.